Okay, so there's a couple examples here that we have to go through. Now this is like step 2 of your Ohm's law progression. So the first step, we get you familiar with series, parallel, and then the combination circuits, and we're always giving you the various resistances. And the twist on this one, which is why it's a bit of a problem, is it's possibly the first time that people have seen a resistance not given. But if we don't give you something, we have to give you something else, or else you can't solve this thing. So we don't have R1 here, but we give you this 3 amps here. And what I'm going to do is put our givens in orange, so we know that those aren't wrong, and we'll do all of our calculations in another color. So the first thing to recognize is, where does this 3 amps go? Right? So hopefully everyone will figure out that that 3 amps is the total current. Now, whether you recognize this right now and pen it in, or later, it doesn't much matter, but you're going to also have to recognize that if 3 amps is the total current here, 3 amps is also going through R1, so you can put 3 amps here. You're going to have to remember that, or notice that sooner or later. Now from here, why I like these calculations are, you can see readily, if I have 3, I can get the 4th one, or along the rows, if I have 2, I can get the 3rd one. So it kind of gives you an idea of what goes next. Now this is optional, but I always put this in order to help people understand how you attack these combination problems if you're having an issue. So you'll see me, and I always write this little formula down in terms of resistance, because that's how we're going to attack it. So total resistance, if we had it, would be R1 plus this part, which is in parallel. So we have to do this parallel portion first to get an equivalent resistance, and then we're just going to add it to R1. So we put the brackets in, and it's R2, and the only thing you may not have seen before is just the parallel train tracks. That just means that whatever's on the left is in parallel with whatever's on the right. That's all it is. It's just an explanation of how we're going to attack it. So you can see right away, we've got to deal with this part first. Can we? Yes, we have these values, right? So you can figure that out here as a first pass. We don't know R1, so we're going to have to figure that out. But this is an explanation. And then you just work with the values given. Now, if you look down here in the chart, you can see you can use Ohm's law to find RT, because you have VT and IT. So RT equals VT over IT, which is 12 over 3, which equals 4. And these were all base values, so I just leave them out. So this is a base value of 4 ohms is the total. All right, so that's the total. I'm going to pen that in, and because that's a calculation, I'm going to put that in black here in case we get it wrong. But you can see what we really need to find next is R1. So how do we do that? Well, we know the total resistance of this circuit is 4 ohms. We just calculated that. We can calculate the resistance of this piece right here, R2 in parallel with R3. Now you can go ahead and calculate it. There's a bunch of different ways, but if you have a resistance in parallel with itself, that portion, that's the equivalent. I'm just going to put it here. I will put it right here. That's the equivalent of 2 ohms. That's the equivalent of those guys. So if you have this equivalent, just let me bring this down here, because it probably would be worth looking at. RT equals R1, which we don't know, plus, now this mess, we just did it. It's 2 ohms. So move this around a bit, and we know RT is 4. So we could put 4 equals R1 plus 2. And if you just switch this around to get R1 on the left, in this case R1 is on the right, it's a little bit easier to say R1 equals 4 minus 2, R1 equals 2 ohms. And that's how that's done. And this is where people are probably getting a little hang up. You're just, when you don't have this, you're stymied. And if you don't know where this 3 amp goes, it's not going to help you a whole lot, because you got to get it down here in order to find IT, and then you've got to, RT, then you've got to back out R1 from that. But it's just straightforward. I intentionally gave simple numbers. So could this be done in your head? Absolutely. If you understand this, these numbers are simple enough to do the math in, that you could definitely do it in your head. So if I put R1 as 2 ohms here, because that's what we figured out, you know right away, V1. V1 is simply I1 times R1. All right, and that's simply going to equal 6 volts. So I'm going to put 6 volts here. And all right, and what's next? Well, you can't use Ohm's law because you don't have any 3 of 4 on the columns or 2 of 3 on the rows. So you have to understand the characteristics of the circuit you're looking at. Let's look at voltage. We know that R1 is 6 volts. If I start out with 12 and I lose 6, and the entire rest of this is just a parallel circuit and a single resistor in each of these 2 branches, you know these each get 6 volts. All right, that's just simply knowing the characteristics. And this next piece, to figure out the current, you can do it 2 ways, whichever you find easier. Now, looking at the simple math, it's easy to figure out which way you should go, and understanding that these are both the same resistances, which makes this whole calculation a lot easier. I've got 3 amps going down here. It's going to split Kirchhoff's current law. Well, current going into a point equals the current going out of the point. 3 amps going in means I need to have the sum of these 2 branches at 3 amps. And because they're the same resistance, and they're the same voltage, obviously, they're going to be the same amount of current flow. So 3 divided by 2, 1.5 amps, 1.5 amps. How else could you do it? Another way, if you didn't recognize that and these weren't the same and you couldn't take that easy shortcut. Well, you've got 6 volts and you've got 4 ohms. You simply do I equals V divided by R. 6 divided by 4, it goes in 1.5 times. And you'll notice it's the same for that. All right, so that's the straightforward situation that is with this. I think what's going to throw people, possibly 2 things. They don't have this resistance here, and they're used to being given that. All right, so as soon as you throw the slightest curveball at people, they tend to fall apart. We don't give you that resistance. We've got to give you something else, or it's not solvable. And we give you this 3 amps. So the next hang up is knowing where to put this 3 amps in here. And then from there, you just simply look at rows and columns. Can I do Ohm's law, or do I need to revert back to a characteristic? And if I've got all these resistances but this one, I can calculate this one based on nothing more than the total resistance that we calculated and these 2 resistances, because you know how they react mathematically and how they are positioned within the circuit. This guy is in series with everything else. It shows up there. That's why I do that. It's just an explanation. And that's that one done.